Okay, Ted, we're going to talk about rasterization now. This is actually my second attempt at this lecture. I got about halfway through and we had power failure and lost all of what I had recorded. So we'll start again at the beginning. So what I mostly want to focus on is how we get fragments when we finally get past the clipping stage and how we rasterize in particularly line segments and polygons. And we'll look at two principal algorithms for drawing lines, the DDA algorithm, which is sort of the classic, very straightforward way to look at it, and Bresnahan's algorithm, which has some very remarkable properties and probably is the one that's built into all of the CPUs and pretty much anything that's going to generate fragments from line segment specifications. Then we'll turn and use that and turn to looking at how we can extend these ideas to polygons. And at the very end, I'll talk a little bit again about aliasing and anti-aliasing. We've already talked some about that, but we'll come back to that. So historically, rasterization was called scan conversion because of the idea that you worked line by line as you generated the display top to bottom on older systems. And so given some primitive that specify a set of vertices, the idea is to produce all of those fragments that are inside. For a line, we could say they're the fragments that are in between the two vertices for its endpoints, and obviously for something like a triangle, we understand what the inside is. We have to fill all of those pixels. Now, what we're not going to worry about are other attributes like color and texture, because once we have a pixel location and we generate a fragment and that location goes and generates an instantiation of a fragment shader, we'll set the color and the texture in there. So we sort of know how to do that. The problem is at this point is what goes on inside of the rasterizer that says which are the fragments that are going to be generated. So let's start with a very simple view of how we can rasterize a line segment. And let's assume we start with in some kind of window or screen coordinates, so we have integer values for the endpoints of the line segment. And right here we're going to assume that when you take those integer locations, they correspond to these points in the frame buffer, which you have coordinates 0, 1, 2, 3 in the x direction. Actually, in reality, these will correspond to the center of the pixels. So when I send 1, 1, 1 to a rasterizer, it's really in the middle of a pixel, and you can think of the coordinates perhaps really, and we'll see this in a few slides, of really being a half, but they're specified in integers and they refer to the center of a particular pixel. So a very simple way to generate this line segment would be to say, okay, it has the coordinates y equals mx plus h. We start off at these two integer locations, where if we had started with floating point, I could always round them up to integer values. That's not a key issue at this point. And how do we march along this curve? Well, it has a constant curvature, or a slope is a constant, and the slope is given by just the difference of the y values at the endpoints and over the difference of the x values at the endpoints. So the slope is delta y over delta x for any 2 points that are along that line segment. We can compute it from given the starting points. Now, the original algorithm and the one on which pretty much everything is based is called the digital differential analyzer algorithm. The DDA was an old mechanical device that goes back to World War II, which they used to solve get numerical solutions to differential equations, generally for solving for things like bomb trajectories. And it was a mechanical computer because it predated the age of real digital computers, and it was constructed with gears and shafts. And you can think of each tooth on a gear as being some sort of a counter where you count the number of gears, and therefore it's kind of digital. And you can think of a row of gears as being some sort of register with integer values. And these things would just grind along. They were very large. They took up a huge space, multiple tables. You can still find some of them in science museums that have preserved them. And so what they were doing was solving the simple differential equation that you get by looking at the equation for the line y equals mx plus h and differentiating it with respect to x, and you get dy dx is the constant m, which is delta y over delta x. So it's a fancy name for a very simple thing, but historically it was important. Now suppose what we do is we're on a scan line, and I have let's do it this way. Suppose I go along in the x direction, incrementing x by 1 each time. So what I'm going to do in terms of this picture in the frame buffer is just go from the original x1 to x1 plus 1, x1 plus 2, until I get down to the final x. And for each of those x's, I'm going to find the y by sticking it back in this equation, or better, I'm going to use this fact that if delta x is equal to 1, then delta y must be equal to m, and so every time I step to the right in x, I'm going to step upwards in this case by a value of m. And so that's a very, very simple way to get the solution, but the part that's going to be a little tricky here is that delta y and delta x are integers because we start with integer values for the endpoints, but their ratio is going to be a float. So we'll have to do something like in this little sort of pseudocode loop. We march from the first x to the last x, and we increment x by, let's say, 1 each time. We increase y by m each time. Now this is a float, while these guys could be integers, and then I have one simple function that writes a pixel, or in the case of the pipeline, it creates a fragment with the coordinates x and the rounded y, so I can get the nearest integer value is essentially, and then I send out whatever the line color is, or leave that up to the fragment shader. So in a way, if you look at that algorithm, it's saying for each x, give me the closest y. You increase by m, and you find the closest y, and you say, oh well, in that case it's this value over here for the center of a pixel, and the next time, well, it's a little, here it's kind of in the middle, it might be this one or this one. So the algorithm could sort of in words be, for each x, find the best y that you can. Now that's pretty simple, but it has a problem, one of which is that if you march along with a slope that's fairly low, then you get these jaggedness, that's the aliasing issue, but you get pretty good little approximation to the line. But if you have a very steep slope, then what happens is you keep getting the same pixel for a while, and then all of a sudden you get this one, and there's this jump, and it really looks lousy, and then when you get up to a vertical line, vertical line, it simply doesn't work. You just don't have pixels. So this algorithm is a start, but it isn't quite what you want. But what you can do is you can use some symmetry here, and you can argue that, well, look, let's say if the slope is bigger than 1, so that would be the 45-degree line here, what I should do is just reverse the equation and say, for each x, give me the closest y, and swap that for each y, give me the closest x, and then I get something that's symmetric this way with what I had down here. And you could take care of the cases with negative slopes with this kind of using again this kind of symmetry argument. And in fact, that's what's done, and this restriction of the slopes to be between 0 and 1 is going to be crucial for Bresnaham's algorithm, which is what we're going to do now. So let's look at Bresnaham's algorithm. Let me give you, so what the problem I'm trying to get around here is that the DDA algorithm required a floating point addition for each step. Now that may sound like not very much, but the problem is that it's floating point, and if you're going to try and put this in microcode, then the floating point is a much more complex thing to do than to have integer values. So the amazing thing about Bresnaham's algorithm is it'll turn out to get rid of all floating point operations, which I think is absolutely a remarkable thing. The other thing that's very interesting about this, for this being a UNM course, is Jack Bresnaham is actually a UNM graduate way back in the 50s. He actually came here as a football player, wound up as an EE major, then went to work for IBM, and he created this algorithm for use with printers. That how do we figure out where to put the dots on a printer? That it was built into all of the IBM printers, and then when we started getting graphics with CRTs and other things, that it became the standard algorithm when we started having digital displays. And you could argue that it's probably the most widely used algorithm in the world. When I discovered that Jack had been a UNM grad, we actually had him come back as an outstanding graduate and talk to our students. He had been retired by that time. So it's a really interesting algorithm. There's a later version he did for circles that works pretty nicely. Same kind of argument. So let's do this. Let's start by assuming that the slope has to be between 0 and 1, because we know we can get the other cases by symmetry. We can, if the slope's between greater than 1 and positive, then we can just switch the roles of x and y. And we're going to assume, as I said a few minutes ago, that the centers of the pixels are at the half integers. And that's really what happens, and it turns out that's an important distinction for aliasing kind of considerations in hardware. So if we say that the slope is between 0 and 1, and let's assume we just finished deciding on we're going to put out this pixel or this fragment at a certain location, how many choices do I have for the next one? As I move one to the right in x, how many different y's can there be, or how many choices are there for the next pixel? And it turns out there are only 2, because the slope is restricted to being between 0 and 1. To get up more than, you can't go down in y, and you can't go too far up because the maximum slope is 1. And that's the key issue, because two things. We're going to start looking at things. One is that the slope is restricted. We have few choices. And the second thing is that we're going to look at things incrementally. And we started doing that in the last lecture when we were talking about hidden surface removal, is when we use the differential form for moving across a flat surface. Things became much easier. And in fact, that's going to be exactly the case here. So here's a pixel. It's centered at here's the one I assume that I already put out. And it's centered at I plus a half, j plus a half. And the only 2 candidates I have for the next pixel are the one going right to the right and the one right above that. Now, if I only tell you I know only about this pixel, here's the line, but I don't really know where the line is. I just sort of have its parameters, and I know I just put out this pixel. What I want to avoid is evaluating this equation because of the floating point operation. So I'm going to say, well, gee, if this is these are the only 2 possibilities that I have, let's look for some sort of decision variable that'll say, if this variable is bigger than 0, then I'm going to do this one, and if the variable is less than 0, I'm going to output this one, and then move on incrementally once I've done that. So that's the basic idea here. And if we get the equations sort of in the following way, if I look at the line and I say, well, what's the difference between the line and the center of the pixel with the same y, and the difference between the line and the pixel at the next 1 pixel over at I plus 3 halves, and the pixel one above. So that one distance is A, one distance is B. And the argument is, look, if A is bigger than B, then I'm going to put the next pixel is going to be this lower one, and if B is greater than A, then I'm going to do the upper pixel. So the decision variable, you can say, is B minus A, and if B minus A is greater than 0, then I'll use the upper one, and if B minus A is less than 0, I'll use the lower one. Now the problem is, if I compute B minus A by using the equation of the line, I have floating point in there. But if you look at it carefully, and this is in the book, it turns out that the only thing that makes it floating point is the denominator in the equation for D has a delta x in it. If I multiply by delta x now, I get a fully integer expression, and an expression which, well, easy to evaluate because it's totally integer. And so we make the decision variable delta x b minus a. And because delta x has to be positive, then this has since it's a decision variable, it doesn't really matter how positive or how negative it's going to be. I only care about the sign. And that's the other big trick in Bresnahan's algorithm. By multiplying by this delta x, everything becomes an integer expression. Now, if you look at the expressions for b minus a, they're a little ugly, bunch of integer multiplication. But what we really want to know is what happens to d as I go from the choice I made over here for the pixel at x equals I plus a half to here. I look at it differentially. So if d of I is what I computed here, I want to know how I get to d of I plus 1 where when I've moved over 1 to the right. And if you do that, it turns out these equations become remarkably simple. They simply involve taking the previous value, and depending on whether it was less than 0 or greater than 0, I either decrement it by 2 delta y, or I decrement it by 2 delta y minus delta x. So it turns out to be, which actually can be as positive. So this is fully integer. It requires essentially no work. Multiplications by 2 are just shifts. And so I have to do just this little subtraction over here and a test. So this is actually reduced to a single instruction on a graphics chip, that for one instruction, just like an instruction that carries out an arithmetic operation, there's one instruction to generate a new point using Bresnahan's algorithm. So it's remarkably efficient. It's been used for years and years now. This goes back, I think this was done actually in the 60s sometime. So it's been around for a while. There are variants that take care of issues like, I haven't talked about the initial value. We haven't talked about the fact what happens if the vertices you start with are not located at the center of pixels. All of those things can be added in. But these basic ideas are really nice. And it sort of shows you, even when you start off with something that looks fairly simple, you can actually often get something that's actually much better than what you started with. So let's look at the next now turn and look at polygons. So for polygons, let's start with the idea first that scan conversion means fill in terms of when we're talking about polygons. And the biggest problem is to start with, if I take the most general polygon, which isn't necessarily convex and isn't necessarily simple, edges can cross other edges, then you have to make some decisions about what's, convex, as we'll see, is easy, what's inside and what's outside. And that's kind of tricky. And you have multiple ways that you can define it. So one way we'll look at in a second is called the winding number. It's sort of what you get when you start circling around the polygon in some direction. So let's assume that this example here, the star, starts with 5 vertices, and I go, so let's start up here on the left, the upper left. I go then to this vertex, then I go to this vertex, this one, and so on. What happens to this area in the center because of this? The edges are crossing each other. I might just as well have decided that I want to color the inside and not have it be interpreted as the outside as I've drawn it over here. This would be the result where you have odd, even fill, where the notion of odd and even might be that if I draw a scan line, if we're going to do this scan line by scan line starting at the top, if I take a scan line like at the top right through here, well, it's simple. I just have crossed into the polygon and then I leave the polygon. That's easy to tell by just looking at the directions that I'm traversing the outside. So if I traversed it as I drew it before, I went this way, there. So I'm coming down here, I go inside, then I cross an edge that's going up over here, so that must mean I'm outside. So if you look at odd, even, if I've done an odd number of crossings, I'm inside. If I do an even number of crossings, I'm outside again. That's even easier than looking at directions. I've crossed once, so I'm inside. I've crossed 2 edges, I'm outside. Argue the same here, that I go inside, outside, outside. And then if you're coming across the middle here somewhere, let's draw it like this. Now you can argue you're going inside, outside. Now the center would be interpreted as being outside and would be not filled. Other ways, as we'll see, depend on the winding number. So let's look at that. That involves going around in a certain direction. So if we now look at a point that's inside, and we want to decide, oh, let's look at a point and now decide if it's inside. So we can argue the following, that if we start encircling the point, and that's what's going on here. It's sort of something, it's like when you topologically, like when you study knots, which some people do. If you encircle the point clockwise or counter, let's do it here clockwise. So you're going around this point, and notice it's really only encircled once. You go up here, around here, so it's really encircled only once, so that's its winding numbers 2. If you look at this point over here in the center, it's circled once, and then you come back and you circle it again, so its winding number is 2. So one argument would be to say, well, we're going to color it, decide it's inside and color it if its winding number is anything but 1. So instead, so in our previous slide, we said, oh, we did inside, outside, so this is now not filled. Here we observe that the winding number, which really, if you draw a line, all you have to reel through here, all you have to do is look at the directions of the edges that it crosses to get the winding number, and just say if the winding number is greater, not equal to 0, then you're inside of the polygon. And this ties together with the notion of tessellation and tessellation shaders that I brought up very briefly in a previous lecture. Now, if you want to do this inside the frame buffer, which probably makes more sense, then you're only dealing with things like triangles, and it's fairly easy to do. You're basically doing inside-outside kind of testing. You enter the polygon until you cross another edge, because it's convex. You're going to go in once and out once, so you should be okay, and then you can do your shading in your fragment shader as you do that. And if you combine that with what we talked about last lecture about the Z-buffer algorithm, everything becomes incrementally. You march incrementally across a scan line. You incrementally look at how the depth changes and make the decision about whether it's obscured by another polygon or not. So that's pretty easy to do. If you start looking at interpolation, so here's sort of how you would get the scan line and how you would find the edges from this. So you would interpolate, you can interpolate between 2 edges to get this point C4, and obviously interpolate between C2 and C3 to get this C5, and then just interpolate across to get the fragment location. So if you were up here, you would use the interpolation between C1 and C3 to get a start point, and the interpolation between C1 and C2 to get the end point where you left the triangle. So you have to basically keep track of where the Y changes and keep track of this vertex. So basically, it's fairly simple to code and put that into hardware. Okay, a couple other ways to look at it would be to do something like this. This is cute. And actually some of the old hardware did this. I used to have a workstation, original Sun workstation that was using this kind of an algorithm. If you argue the following, we can argue recursively. We can say, if I know a point that's inside, okay, let's suppose it starts, and I draw all the edges, okay, so this can be done right in the frame buffer, so the edges are black. What you can start doing is saying, well, if I'm inside, what I'm going to do is look at the value and decide, well, if it's white, then I'm going to make it black because it's an inside point. And then I'm going to execute the same algorithm all around me. 1 point above me, 1 point below me, 1 point to the right, and 1 point to the left. And this will eventually stop because you're going to hit edges. So whenever you hit an edge, the recursion stops, and eventually everything is filled. Now, there's a couple of little issues with this algorithm. Is the recursion can be very slow, and it can put an awful lot of pixels onto the stack. But it is an interesting technique, and you can de-recurse it. I mean, that's one thing people will do, is take an algorithm like this and take out the recursion, make it iterative, and then it'll be much more of a reasonable algorithm. Practically, there were some issues with this kind of algorithm, because if your edge wasn't absolutely perfect, you could actually escape the inside, and then it would start filling your entire screen in an older system where fill was fairly slow, you'd see it slowly overwhelming the screen as it did this recursion. But it's a nice starting point for a number of algorithms. There's some algorithms about where you're trying to look for obstacles that turn out to be very close to this. You start flood filling to find the shortest path through a bunch of obstacles, and it's almost the same code. Another slight variation on this idea is to what's called scanline fill. That when we talk about scanline algorithm, I think it was the last lecture, this ties in with that you build some sort of a data structure that tells you how to fill the thing scanline by scanline. So the idea was this: if I start with a polygon specified on the left by vertices A, B, and C, then the way I would incrementally generate the vertices, at least in a clockwise order, would be to march along in between A and B, generating the location of vertex 1, 2, 3, 4, 5, 6. Then I'd march along from B to C, getting 7, 8, and 9, and then finish it by going from C to A to get 10, 11, 12. Now the problem is that's not the order in which I want to fill if I'm going to work my way down scanline by scanline. So when I get, for example, so here's nothing's going to happen, here nothing's going to happen. Here, well, that's okay, 6 and 7 are next to each other, but you see what happens down here, 5 and 8 are not. And so getting the proper vertex for the end of I start filling here to get the proper vertex for the end, they're just not stored in the right order. What I really want to do is have the vertices stored 1, 2, 3, 4, 5, 6 this way, so that I can go, knowing this is a convex object, knowing I go from 1 to 2, then 3 to 4, 5 to 6, and so on. So what you generally want to do, and this will work even if it's a non-convex polygon, is to build up a data structure that stores it for a given scan line, and this could be coupled with what we were talking about last lecture. So you have a scan line, so in one direction you're having scan lines. The scan lines each have a linked list of intersections, and these lists are fairly long, so you can do an inefficient sort, like an insertion sort, to get these in the proper order. So if you get to a scan line where if you have a non-convex polygon, you enter, you leave at x5, you enter again at x7 and leave at x8. As you generate this data structure, you do an insertion sort on this linked list, which isn't too bad. And that's not a bad algorithm, gets used and still gets used in some contexts. Okay, so finally let me finish up by saying just a couple of words again about aliasing. Just a reminder that we would really like to have a 1 pixel wide line, and everything we've done now has said either for each x find the best y, or if the slope was greater for each y find the best x. Well, that's sort of guaranteed to give us a alias jagged line, because for you're not distributing the color. You're saying it all has to be like right here, either in this pixel or in this pixel. You can't do partial coloring, and that produces the jaggedness. And here's kind of what you would generally see for that. I don't know what I scan these off of. And so what you really want to do is do something that sort of averages these out a bit and distributes the color among different values. Or for example, in this example, I would like to distribute the value maybe half in the lower pixel and half in the upper pixel. And there are many ways to do that. It was built into desktop OpenGL. A lot of times now it's just built right into the hardware, so you get a blurrier line. You could also look at it as kind of filtered to smooth out the jaggedness. It's doing a little better than just that, because a horizontal or vertical line will come out perfectly anti-aliased or not anti-aliased. For polygons, you have some other sort of more annoying kinds of issues. So here's a little picture to finish this off with. This is an argument that you really need some sort of compositing to be done right, because if you have these polygons, one problem is if they all look at this pixel here, where all three of this little bitty polygon, these other two enter all cover parts of this pixel, but I can only assign one color to the pixel. What will happen with hidden surface removal is that you will assign the color of the front one, and it's sort of the very basic approach. You would assign the color of the first one to color this entire pixel. Now that's going to cause jaggedness to all of these. The other problem is that this little, okay, just had a little crash on my very last slide of this lecture. So what we're talking about is this little guy over here, and all I wanted to finish up by saying was that if this was, for example, the front in front of these two, it would totally dominate this area, which would also be kind of wrong. So one of the problems would be that if it was behind them, you'd start seeing flicker, you'd see some weird kind of stuff in an animation. So you really want to do some sort of anti-aliasing. Here it would be based on compositing, because if I made this color depend on the area that each of these three polygons subtended in this fragment, then I would get a blended color, which is going to look a lot better. And so we really want to use that. Compositing is really a kind of better way to look at how you do aliasing when you're dealing with polygons. So this is about it that I want to say with rasterization. We may talk a little bit briefly about points. We haven't talked about points, but if you anti-alias points, then you spread that single pixel around, and they look rounder and they look better. Desktop OpenGL lets you actually anti-aliasing points, lines, and triangles of polygons separately decide what you wanted to do. In WebGL, coming from OpenGL ES, points are called point sprites, and you have some flexibility about how they're done, and it turns out you can, because they're generating fragments, they can be lit just like any other primitive. They're not just a single color that's put on the screen. They're actually an entity that becomes one or more fragments, and those fragments can be texture mapped. You can texture map to a point. They can go through lighting and shading like anything else. So the only other lecture I want to give about these kind of issues, I want to talk more about what happens on the display and look a little more at what happens with color, and I think that's going to be very interesting.